Hello all. Today we will discuss about implementation methods, that is implementation methods of different programming languages. And as we know that two main primary components of a computer are its internal memory and its processor. And what is the use of internal memory? That is used to store programs and data. And what is meant by this processor, or what constitutes this processor? So basically it is a collection of circuits, okay, and this collection will actually give us a realization of a set of primitive operations or machine instructions, such as we have arithmetic and logic operations. And in most computers we can call some of these instructions as macro instructions, and these macro instructions are actually implemented with a set of instructions. They are called as micro instructions, and then again we can define them at even lower level. And the machine language of the computer is it's a set of instructions. Okay, so machine language of a computer means we have a set of instructions. And in the absence of other supporting software, its own machine language is the only language that most hardware computers understand. As we know, even though we have different high-level languages, or even we have assembly languages, etc., but still the machine can understand only the machine language. Okay, that is actually a set of or a language consisting of zeros and ones. Okay. And a computer could be designed and built with a particular high-level language as its machine language, but it would be very complex and expensive. We can theoretically say like this: that is, a computer could be designed and built with a particular high-level language as its machine language, but it's very complex and expensive. And it would be highly inflexible because it would be difficult to use it with other high-level languages. Okay, we are not saying that all these things are not are impossible, but it is very difficult to use it with other high-level languages. And the more practical machine design choice implements in hardware a very low-level language that provides most commonly needed primitive operations and requires system software to create an interface to programs in high-level languages. So what actually we do is, it's very difficult to implement high-level languages that the machine understands. But what we usually do, or the practical solution, is that we have some hardware there, and we have a very low-level language, and that will provide most needed primitive operations. But we need a system software. Okay, and the system software's duty is to create an interface to programs in high-level languages. Okay, so a language implementation system cannot be the only software on a computer. Also requires a large collection of programs, and that is known as operating system, and which supplies high-level primitives than those of the machine language. Okay, and these primitives provide system resource management, input and output operations, a file management system, then text or program editors, and a variety of other commonly needed functions. Okay, so we have, what we say is that we have a language implementation system, but that is not the only software on a computer. So we have an operating system also there, and that will actually provide high-level primitive operations. Okay, for example, like resource management, how to manage all the resources like processor, memory, and input and output operations or file management, etc. And because the language implementation system needs many of the operating system facilities, they interface with the operating system rather than directly with the processor. Okay, that is in the machine language. Okay, so the operating system and the language implementations are layered over the machine interface of a computer. Okay, and these layers can be thought of as virtual computers, and they will be providing interfaces to the user at high levels. Okay, for example, we have an operating system and a C compiler which provides a virtual C computer. And with other compilers, a machine can become other kinds of virtual computers. Okay, suppose we have other compilers, then the machine can become other kinds of virtual computers. And most computer systems provide several different virtual computers. And user programs from another layer of the top of the layer of virtual computers. And this layered version is there, and you can see that before coming to this, let's see the implementation systems of the first high level programming languages were among the most complex system software of that time. Okay, that was in late 1950s. And in the 1960s, intensive research efforts were made to understand and formalize the process of constructing these high-level language implementations. Okay, and the greatest success of these efforts was in the area of syntax analysis. Okay, and primarily because that part of the implementation process is an application of parts of automata theory and formal language theory. Okay, so that's why many intensive research efforts were made to understand and formalize the process of constructing this high-level implementations, and that actually brought light into the syntax analysis. Okay, and we'll first look at the compilation. Okay, programming languages can be implemented by any of three general methods. Okay, at one extreme, programs can be translated into machine language, which can be executed directly on the computer. Okay, that is one extreme. We have three general methods. So the first method says programs can be translated into machine language, and this can be executed directly on the computer. And this method is called a compiler implementation. Okay, and it has the advantage of very fast program execution once the translation process is complete. Okay, this is compiler implementation, which means these high-level language programs can be translated into machine language, which can be executed directly on the computer. Okay, and most production implementations of languages such as C, COBOL, C++, and ADA are by using compilers. Okay, and the language that the compiler translates is called the source language, and the process of compilation and the program execution takes place in several phases. Okay, so we have this kind of a compiler, and the language that the compiler translates is called the source language. Suppose you have written a program in C language. Okay, that is your source language. Then the process of compilation and program execution takes place in several phases. We have mainly 6 phases, and there are 2 supporting phases also. Okay, so that is shown here. We have the source program, then we have lexical analysis, syntax analysis, and 2 phases are combined and written here. That is intermediate code generator and semantic analyzer. And we have code generator that will generate the code, the final code. And before that, this will be given to, that is the intermediate code will be given to the optimization module or optimization phase, and that will optimize this code, and that is taken as the intermediate code, and that is given to the code generator. Okay, and we can say that the optimization is optional, But if you do optimization, your overall execution speed will be very high. And we have code generator, and this code generator will convert the source language program into a machine language program. Okay, and that is fed to the computer, and you are giving the input data, and that will print the result. Okay, and we have a symbol table also. Okay, the symbol table is all the information about the variables. Your program variables will be stored in the symbol table. The symbol table contains different kinds of information like variable name, variable type, their scope, everything will be written here. That will be stored in the symbol table. Okay, and all the phases which need all this information will take it from the symbol table. Okay, so the lexical analyzer gathers the characters of the source program into lexical units. So this is the first unit, that is lexical analyzer. Input to this lexical analyzer is your source program. So it gathers the characters. So when a program is given to this lexical analyzer, it reads this program character by character. Okay, then this will be grouped into lexical units. These lexical units are otherwise known as tokens. Okay, the lexical units of a program are, for example, in C language you have lexical units or tokens, like you have identifiers, special words, operators, or punctuation symbols, so and so. Okay, so the lexical analyzer ignores comments in the source program because the compiler has no use for them. Suppose you have written comments in your program, the lexical analyzer will just ignore that because there is nothing to do with that compiler. That is, the comments are given for understandability. Okay, and after this lexical analysis, the output is this reads the source program character by character, and these characters are grouped into tokens or lexical units, and these lexical units are given to the next phase, that is the syntax analysis phase or syntax analyzer, that takes the lexical units from the lexical analyzer and it uses them to construct hierarchical structures called parse trees. Okay, so they use these lexical units and it builds a parse tree. Okay, these parse trees represent the syntactic structure of the program. Okay, so here it checks the syntactic structure of the program. What is meant by the syntactic structure? That gives how the structure of a sentence. That is, for example, if it is a variable declaration, then you must first give this data type for this variable, then you should supply the list of variables. If you have n variables, they all should be written by separating them using comma. And finally, after the last variable name, you should put a semicolon. That is a syntactic structure. So these parse trees represent the syntactic structure of the program. And actually, in many cases, no actual parse tree structure is constructed. Rather, the information that would be required to build a parse tree is generated and used directly. Okay, usually what information is needed for constructing this parse tree? So all this information will be gathered and that will be used directly. Okay, and both we have this lexical units are there, and that means they are the tokens, and these tokens are combined to form sentences. Okay, sentences of your language or sentences in your program. And these parse trees are given to the intermediate code generator. Okay, so intermediate code generator produces a program in a different language at an intermediate level between the source program and the actual output of the compiler. So it is an intermediate representation, which means it is intermediate between the source program and the final output of the compiler and the machine language program. So intermediate languages sometimes look very much like assembly languages. Okay, so these intermediate languages look very much like assembly languages and sometimes are actual assembly languages. Sometimes they could be assembly languages also. In other cases, the intermediate code is at a level somewhat higher than an assembly language. Okay, sometimes this the assembly language is somewhat lower. So your intermediate code will be somewhat higher than this assembly language. And the semantic analyzer is an integral part of the intermediate code generator. And the semantic analyzer checks for errors such as type errors that are difficult to detect during syntax analysis. Okay, usually the duty of the semantic analyzer is that it will check meaning of semantics means the meaning. Okay, so it will check semantics of your input program. Okay, semantics means what is meant by that sentence or that program. Okay. Usually different types of semantic checks are there. One of them is a type checking. Type checking is usually when you have an expression and or expression or that consists of operators and operands. In that case, usually type check checks types of each of these variables. For example, suppose I am giving A is equal to B mod C. What is meant by that? A is equal to B mod C means B mod C is B will be divided with C and the remainder will be given to A. So A mod C. And here the condition is that when you give A is equal to B mod C, suppose A and B are of the type integer. Okay. Or you should ensure that this modulus operator requires both of its arguments or parameters or operands as of integer type. Okay, so the type checking or semantic analyzer just verifies that types of A and B or B and C are of the type integer and type of A is also integer. That's what this kind of a type checking. Okay, that is one kind of a semantic analysis. And we have, after this we have optimization, and as I told you before, this improves programs, usually in their intermediate code version, by making them smaller or faster or both. And that is often an optional part of compilation. Okay, so we have this optimization that will make your code smaller or faster or even both. Okay, some compilers are incapable of doing any significant optimization. Okay, this type of compiler would be used in situations where execution speed of the translator program is far less important than compilation speed. Okay, sometimes what we need is the execution speed. We don't care about the execution speed, but what we need is we need to have a fast compilation. So in that case, usually we'll skip this kind of code optimization. Okay. And for example, in a computing laboratory for beginning programmers. Okay, so we have a beginning programmers and there is a computer laboratory in this beginning programmers. So there they focus on what? They don't bother about this execution speed, but they bother about compilation speed. Okay. In most commercial and industrial situations, execution speed is more important than compilation speed. Okay. In commercial purposes, what we need is we need to have a high execution speed. Okay, it should be higher than the compilation speed. In that situations, compilation or optimization is routinely desirable. And because many kinds of optimization are difficult to do on machine language, most optimization is done on the intermediate code. Okay, so if we have a machine language and we perform optimization, that will be very difficult because machine language is always with the zeros and ones. So what we do is we have an intermediate code representation, and this we perform optimization on this intermediate code. Okay. And we have the code generator that translates the optimized intermediate code version of the program into an equivalent machine language program. And we have the symbol table that serves as a database for the compilation process. And the primary contents of the symbol table are the type and attribute information of each user-defined name in the program. Okay, user-defined name in the program means they are the variable names. Okay, and this information is placed in the symbol table by the lexical and syntax analyzers, and that is used by the semantic analyzer and the code generator. So mainly this is this information, that is name and type of this variables. These are entered by lexical and syntax analyzers, and they are used by this semantic analyzer and code generator. And although the machine language generated by a compiler can be executed directly on the hardware, that's what we claimed, it must nearly always be run along with some other code. Most user programs also require programs from the operating system. Okay, so among the most common of these are programs for input and output. So the compiler builds calls to required system programs when they are needed by the user program. So before the machine language programs produced by the compiler can be executed, the required programs from the operating system must be found and linked to the user program. Okay, so that's what we say in most of the cases. We use, or for example, we use some library functions or some library modules. Okay, so before executing this, all this program, we need to link all these modules together with your user program. So the linking operation connects the user program to the system programs by placing the addresses of the entry points of the system programs in the calls to them in the user program. So we have entry points in this of the system programs, and they are linked to, or their addresses will be given in the user programs. Okay, and the user and system code together, are sometimes called as a load module. Okay, or that is an executable image. So the process of collecting system programs and linking them to user programs is called linking and loading, or sometimes just linking. And it's accomplished by a system program called linker. So these duties are done by the linker. So that is their most important duty. So we have collection of user code and system code. System code is what is meant by user code is usually written by a user, and system code is particularly for some performing some operations. Okay, so sometimes you use a library function. Okay, so in your C language, suppose you use a library function, this code or that system code corresponding to this function should be linked to your program. Then only that can be executed. Okay, so that is done by the linker. And in addition to system programs, user programs must often be linked to previously compiled user programs that reside in libraries. Okay, so not just this kind of system programs. Sometimes we have previously compiled user programs and they reside in libraries. So sometimes we need these user programs or these user programs must be linked to this previously compiled user programs. So the linker not only links a given program to system programs, but it also may link it to other user programs. One user program will be linked to other user programs. And the speed of the connection between a computer's memory and its processor usually determines the speed of the computer, because instructions often can be executed faster than they can be moved to the processor for execution. And this connection is called von Neumann bottleneck. Okay, and that is the primary limiting factor in the speed of von Neumann architecture computers. And this von Neumann bottleneck has been one of the primary motivations for the research and development of parallel computers. So when we have this kind of von Neumann architecture, what we bother about is the speed of the connection between the computer's memory and its processor. Okay, and that determines the speed of the computer itself. And because instructions often can be executed faster when they can be moved to processor for execution, because inside this processor we have this registers. So usually we'll bring them into this processor registers, and this connection is called a von Neumann bottleneck. And this is the case with compilation, and we have pure interpretation also. Okay, so pure interpretation lies at the opposite end, that is from compilation of implementation methods. So with this approach, programs are interpreted by another program called an interpreter with no translation whatever. Okay, so the interpreter program acts as a software simulation of a machine whose fetch execute cycle deals with high-level language program statements rather than machine instructions. Okay, so that is the difference. The interpreter program acts as a software simulation of a machine whose fetch execute cycle high-level language program statements rather than this machine instructions. And this software simulation obviously provides a virtual machine for the language. And pure interpretation has the advantage of allowing easy implementation of many source level debugging operations, because all runtime error messages can refer to source level units. Okay. For example, if an array index is found to be out of range, the error message can easily indicate the source line and the name of the array. On the other hand, this method has the serious disadvantage that execution is 10 to 100 times slower than in compiled systems. Okay, because in compiled systems the execution time is faster. Once the compilation is over, then only it will start executing. But in the case of interpreter, as and when you give a source line, a source code line, that will be interpreted. Okay. So the primary source of this slowness is decoding of the high level language statements, which are far more complex than machine language instructions. Okay. And regardless of how many times a statement is executed, it must be decoded every time. That is very important, because sometimes we may be giving a loop, but regardless of how many times a statement is executed, it will be, or it must be decoded every time. Okay. So therefore, the statement decoding rather than the connection between the processor and memory is the bottleneck of a pure interpreter. So in the case of pure interpreter, we have a bottleneck, that is with the statement decoding. So even if you are in a loop, every instruction inside that loop will be decoded every time it sees that. Okay. And another disadvantage of pure interpretation is that it often requires more space. Okay, so it requires more space, and in addition to the source program, the symbol table must be present during interpretation. So that's why it requires additional space. And the source program may be stored in a form designed for easy access and modification rather than one that provides for minimal size. Okay. And some simple early languages of the 1960s, for example, APL, Snowball, and Lisp, were purely interpreted. And by the 1980s, the approach was rarely used on high-level languages. In recent years, pure interpretation has made a significant comeback with some web scripting languages. For example, as you know, the case of JavaScript or PHP, all these are interpreted. So which are now widely used, these languages. And the process of pure interpretation is shown here. So you have a source program and you have an interpreter, and the input is given to this interpreter, you get the result. And the third implementation method is a hybrid implementation system. So some language implementation systems are a compromise between compilers and pure interpreters. So hybrid implementation system lies in between this compilers and pure interpreters. They translate high-level language programs to an intermediate language designed to allow easy interpretation. And this method is faster than pure interpretation because the source language statements are decoded only once. And such implementations are called hybrid implementation systems. Okay, so we have something in between this pure interpretation and compilation. Okay, and it is very faster than pure interpretation because here in the case of hybrid implementation, the source language statements are decoded only once. And the process is shown here, and instead of translating this intermediate language code to machine code, it simply interprets this code. Okay, so that's what it says. It simply interprets the intermediate code rather than translating intermediate language code to machine code. So we have a source program here, and we have lexical analyzer. Again, lexical analyzer gives lexical units, and we have syntax analyzer that will give you the parse tree, and we have intermediate code generator. Okay, so intermediate code is there, and we have this interpreter. So input data is given, and this interpreter will give the results. And some examples include Perl is implemented with a hybrid system. Okay, and Perl programs are partially compiled to detect errors before interpretation and to simplify the interpreter. Okay, Perl is an example. And initial implementations of this Java were all hybrid. Okay, its intermediate form called we know its intermediate form is called bytecode, and that provides portability to any machine that has a bytecode interpreter and an associated runtime system. And together these are called the Java virtual machine or JVM. Okay. There are now systems that translate Java bytecode into machine code for faster execution. Okay, and we have a just-in-time implementation system, that is JIT implementation system, that initially translates programs to an intermediate language. Then during execution, it compiles intermediate language methods into machine code when they are called. Okay, so what this does is during execution, it compiles these intermediate language methods into machine code. They compile this intermediate language methods into machine code. Okay, when they are called. So the machine code version is kept for subsequent calls. And these JIT systems are now widely used for Java programs. And also we have the .NET languages are all implemented with the JIT system. Okay, .NET languages. And sometimes an implementer may provide both compiled and interpreted implementations for a language. Okay, so in these cases, the interpreter is used to develop and debug programs. Then, after a bug-free state is reached, the programs are compiled to increase their execution speed. Okay, so we have actually hybrid kind of thing. That is, the interpreter is used to develop and debug programs. So after debugging or after a bug-free state is reached, the programs are compiled to increase their execution speed. And we have preprocessor. So what is a preprocessor? A preprocessor is a program that processes a program immediately before the program is compiled. Okay, so a preprocessor means before the program is given to the compiler, this processes a program. Okay, and this preprocessor instructions are embedded in programs. So the preprocessor is essentially a macro expander. You can call it as a macro expander. So preprocessor instructions are commonly used to specify that the code from another file is to be included. Okay, so that is the purpose of this preprocessor instructions that are used to specify that the code from another file is to be included. For example, we have #include mylib.h. So this causes the preprocessor to copy the contents of mylib.h into program at the position of the #include. Okay, that is the meaning of this line. We have seen #include stdio.h. Okay, so it says that the contents of stdio.h, that is copied into the program at the position of the #include. Okay, and other preprocessor instructions are used to define symbols to represent expressions. Okay, so we have symbols are used to represent expressions. For example, we can use something like hash define max a comma b, which means if a is greater than b, then it is a or it is b. Okay, that is to determine the largest of two given numbers. Okay, so max is defined based on this. So if it is defined using hash, that is actually preprocessor directive. Okay, so for example, the expression x equal to max 2 into y, then z divided by 1.73. Okay, this would be expanded by the preprocessor to x equal to 2 into y. Okay, greater than z divided by 1.73. If that condition is true, then it is 2 into y. Okay. Else it is set by 1.73. Okay. So that's what a max that takes maximum among between these two, 2 into y and set by. So that is that can be expanded by the preprocessor like this, 2 into y greater than z by 1.73. If this condition is true, then the result is 2, because if this is true, 2 into y is largest, so that will be printed. Otherwise, z by 1.73 will be the largest. So that is given here. And this is one of those cases where expression side effects can cause trouble. For example, if either of the expressions given to the max macro have side effects. Okay, for example, such as z plus plus, it could cause a problem because one of the two expressions parameters is evaluated twice. This could represent in Z being incremented twice by the code produced by the macro expansion. So that is, suppose we have 2 into y. So what happens here if this is expanded like this? So 2 into y will be calculated once and greater than Z by 1.73. This will again be calculated. Okay, if this condition is true, then our answer is 2 into y. So again this 2 into y will be calculated. Okay, so sometimes this can lead to a problem. For example, suppose the first expression was z or y plus plus. Okay, so that will be that will change the value of y. Okay, now again we perform y plus plus means what will happen? It makes a side effect, that is known as a side effect, and that will generate incorrect results. Okay. So these are different implementation methods, and let's move to this programming environments. So a programming environment is the collection of tools used in the development of software. Okay, so this collection consists of only a file system, a text editor, a linker and a compiler, or it may include a large collection of integrated tools. Okay, each accessed through a uniform user interface. Okay. So in the second case, the development and maintenance of software is greatly enhanced. Therefore, the characteristics of a programming language are not the only measure of the software development capability of a system. Okay, and let's look at different programming environments. Okay, so for example, Unix. Unix is an older programming environment that was first distributed in the middle of 1970s, built around a portable multi-programming operating system. Okay, and it provides a wide array of powerful support tools for software production and maintenance in a variety of languages. And in the past, the most important feature absent from Unix was a uniform interface among its tools. Okay, so it didn't have a uniform interface among its tools, and this made it more difficult to learn and to use. Okay, and Unix is now often used through a graphical user interface. Initially, that was with the help of command line programming or command line interface. Now we have actually a GUI, okay, that runs on top of Unix. So examples of Unix GUIs are the Solaris Common Desktop Environment. That is another one is GNOME and KDE. And these GUIs make the interface to Unix appear similar to that of Windows and Macintosh systems. Okay, so now after the introduction of this GUI, this is something like, the appearance is something like that of Windows or Macintosh systems, which has UIs. Okay, and another environment is Borland JBuilder is a provides an integrated compiler, editor, debugger, and file system for Java development, where all four are accessed through a graphical interface. Okay, so JBuilder is a complex and powerful system for creating Java software. JBuilder. So next one is Microsoft Visual Studio.NET. That is a relatively recent step in the evolution of software development environments. Okay, so it is a large and elaborate collection of software development tools and all used through a windowed interface. We have a windowed interface there. And this system can be used to develop software in any of the 5 .NET languages like C#, Visual Basic, .NET, JavaScript. That is, JavaScript is Microsoft's version of JavaScript. And we have F# also, that is a functional language. And we have C++ or CLI. Next interface, programming interface is NetBeans. Okay, NetBeans is a development environment that is primarily used for Java application development, but also supports JavaScript, Ruby, and PHP. And both Visual Studio and NetBeans are more than development environments. Okay, they are more than development environments. This Visual Studio and NetBeans. They are, or you can call them as frameworks, which means they actually provide common parts of the code of the application. Okay, framework means they actually provide common parts of the code of the application. They gives you the code. Okay, so that is about this programming environments. Okay, thank you.